Hello everyone, welcome to the last video on this particular unit. I will start with audio oscillators. We had seen LC oscillators in the previous videos. Now LC oscillators, they are usually used for higher frequencies, but say suppose I want to produce a low frequency output, then using LC oscillators would be wastage of my resources, okay, because the components are costly. Fine, L and C, especially the inductors. So for generating audio frequencies, I can make use of RC oscillators. Okay, they provide good frequency stability and provides you a better output, distortion-less output. With IC technology, RC oscillators can be used easily because inductors of larger values are difficult to make and difficult to fix in also in particular ICs. Two types of RC oscillators we are going to study in this particular video. First one is RC phase shift oscillator. Second one is Wein bridge oscillator. First, we'll just know the basic working principle of RC oscillators, wherein you have an amplifier which will provide 180-degree phase shift, and you will have a phase shift network which is going to provide you another 180-degree phase shift. So total phase shift in a loop is 360-degree. Now the question over here is that in phase shift network, which are the components which are going to be there? Definitely R and C are the components which will be present in the phase shift network. But how many RC networks I need to make use in this particular network so that it produces 180-degree phase shift? That is again a question. Okay. So I need to select R and C in such a way that it should be able to produce 180-degree phase shift at desired frequency of oscillation. Let us consider the first type, that is RC phase shift oscillator. To explain the working, let us consider this, wherein you can see over here there are RC networks. Okay. Now I know that RC phase shift network should produce 180-degree phase shift. So I have used over here 3 RC networks. Okay. And if at all each RC network provides 60-degree phase shift, then 60 into 3 will give me 180-degree phase shift. So this principle is made use in RC phase shift oscillators. Let's have a look at the construction. This diagram over here is basic amplifier and this is your phase shift network. Okay. Again, we are supposed to explain each and every components because it's a construction. R1, R2 is a voltage divider. RECE is basically to provide stability or temperature stability and AC degeneration. What is AC degeneration? This capacitor CE acts like a bypass capacitor. So basically it will bypass directly to the ground AC. That's AC degeneration. Then you have RC over here. Okay, RC provides control over the output voltage. This output voltage is fed into the load via CC, that is your coupling capacitor. Now, output of this particular phase shift network, okay, is given to the base of transistor. But you all know that a transistor model, it has HIE, okay, HIE resistance, which is very low resistance, okay. So what is done is that, see, you can find over here RC, okay, there is C over here and there is R over here, okay, but this R value is not just R, it is R minus HI. Why this HI is subtracted is only because of this, because this resistance, internal resistance of this particular transistor is going to appear in series. If it is going to appear in series, it means that it will be added to R minus HIE. So the resultant that you are going to get from this is going to be just R. Okay. I hope this is clear to you all. So your R should be selected in such a way that it is R dash plus HIE. Okay. Let's move to the working. To begin with, working, noise due to the transistor or the fluctuations due to this VCC will result in random variation of base current. Okay. Now if at all I get random variation in base current, what will happen is that this transistor will amplify them, okay, and it is amplified and will appear across the collector circuit, which is then given to the phase shift network. Phase shift network is going to provide 180-degree phase shift, okay, and another phase shift is going to be provided by this CE amplifier, okay. So the total phase shift in the network is about 360 degrees. RC phase shift network, it helps in determining the frequency of oscillation. What will be the frequency of oscillation of this particular circuit? Also, not to forget, this network uses resistances, okay, and ECS, you all must have studied in ECS about attenuators, okay. What attenuators consist of only resistances, okay, which means resistances reduces the amplitude, or I can say resistances reduces the voltage, okay, and that's what exactly happens over here. Since resistance are used, it will attenuate the output voltage, it will try to reduce. Fine. Now let's have a look at the mathematical analysis. It's simple. There is a transistor over here and there is this phase shift network. Again, I'm going to replace this particular transistor, okay, with the hybrid model. You can have a look over here. You have a transistor, okay. This is a complete model, again complete hybrid model, wherein there is HIE, HRE V out, HFE IB and 1 upon HOE. Again the same assumptions we are going to make this as an approximate model, that is HRE to be very less, therefore HRE into V out will be very less. Then so I can neglect this, so I will remove this particular thing. Then again HOE is very less. If it is very less, 1 upon very less is very more, I mean too much. So since it is too much, what will happen is that this resistance will be too high, so no current will flow through it, or I can say least current will flow through it, so I can ignore it. Fine, the same assumptions. Let's have a look at this particular circuit over here, especially with respect to R dash, which is R minus HIE. As I told you all, this HIE, R minus HIE, will appear in series with that of your transistor. So that is the reason HIE and HIE will get cancelled and you will get finally R. Okay, so you got your RC. Fine. Now another important thing, since I have ignored this and this, I am left out with this current source and RC. I'll use source transformation over here, that is it will become a voltage source of value, this is current, right? So voltage source should be current multiplied by resistance, so it will be HFE IB into RC, this particular source, and in series with RC. Okay, the current direction is downwards, so that is the reason there will be minus and plus for the voltage source. So minus and plus, and as I told you, it will be HFE IB RC. The current directions I have taken accordingly. Okay. Now what you are supposed to do over here is that apply KVL in each loop. Okay. Apply KVL in each loop. Okay. And then get 3 equations. You are going to get 3 equations like this. I have not solved over here because KVL is quite common. You are supposed to solve it by yourself. Please check whether you all are getting this. Okay. And then arrange it in such a way that you know I1, I2 and IB. Okay. 3 currents are there, I1, I2 and IB. I1, I2 and IB. Here 0 I1 I have written because I1 term doesn't exist in the last loop. So that is the reason 0 I1 I have written, because I will require all the coefficients of I1, all the coefficients of I2, all the coefficients of IB. Okay. And how am I going to solve these equations now? By using determinant technique, because all are equal to 0. It's very easy now. What I'll do is that I'll find the determinant. These are all the coefficients of I1, these are all the coefficients of I2, these are all the coefficients of IB. Determinant of that equals 0, and I have used 1 upon omega c as xc because that will be easier for me to write. Okay, jxc, because otherwise I'll have to write j upon omega c, which will be complicated and it will look big also. Okay, this will be easier for me to solve also. Now I have to find out the determinant, and I hope you all know how to find the determinant, but still I'll tell you all. I'm not going to find determinant this way because there are 3 terms, okay, and it will give me 3 values also, which will be big enough. I'll find determinant this way because third term is 0, okay, so it will reduce the number of terms. So it will be this particular term into, leave that particular row, leave that particular column, this multiplied by this, minus this multiplied by this, okay, then minus this particular term, because plus minus plus it is, so minus of this particular term, leave that particular row, leave that particular column, this multiplied by this minus this multiplied by this equals 0. Okay, this is what I just spoke. Okay, please verify. Now you are supposed to solve this. Solve it in such a way that again you separate them as real and imaginary terms. Nothing to worry. I hope the steps are clear to you. Okay, call that equation 4. Now you all know what is to be done because you got the equation 4. What you do is that equate the imaginary term to 0. From that get omega, I mean xc first because xc has omega. Okay, solve, you will get this particular term. Please verify whether you all are getting this. Okay, I'll call that equation 5. Now I have also got a term r by rc over here. So what I'll do is that I'll say that rc is equal to r. I'll use the condition. So I'll get this particular equation. Okay, this is the frequency of oscillation. If at all rc is not given in numericals and all, you can use this particular condition and this equation. Okay. Now let us take the real component and equate it to 0. Equate the real component. So from real components you are supposed to get HFE. Okay, after getting HFE, you know that the loop gain should be greater than unity initially. So HFE will be greater than this particular term. Okay, now again I'm going to make use of the same condition because I have the same ratio R and RC. So if R is equal to RC, I'll get about HFE greater than 56. Okay, let me call that equation 8. With this the mathematical analysis is complete. These are some of the advantages which you all can go through. Disadvantages, I'll just stress on one because that's required. Frequency stability is not as good as Wein bridge oscillator, which we are going to study next. We are going to see how frequency stability is good over there. Let us start with Wein bridge oscillator. Okay, now Wein bridge oscillator, this is the Wein bridge oscillator where you all can see that there is a Wein bridge which you all must have studied in ECS again. Okay, you have Q1 and Q2, that is 2 transistors. Now the very fact that I am using 2 transistors, this transistor is going to provide me 180 degree phase shift, this transistor is also going to provide me 180 degree phase shift. So the total phase shift will be 360 degree within itself, right? Okay. So this circuit uses 2-stage amplifier, this is a multi-stage amplifier and a Wein bridge, that is the RC bridge circuit. Now the RC bridge circuit is a lead lag network. Okay, that is it uses R1C1 and R2C2. Now what is lead lag network? Let us consider if at all R and C are in series, what will happen? Same current will flow through it, right? So that time I'll say that the current will lead voltage. So it's a lead network. Okay, when R and C are in parallel, that time I'll say that the current will lag voltage. So it's a lag network. So R1C1 which is present is a lead network, R2C2 which is present is a lag network. Same with respect to the phase shift also, it lags with increase in frequency and leads with decrease in frequency. Okay, this is the circuit. Now why this particular Wein bridge is used? I have already got 360 degree phase shift by using Q1 and Q2, 2 transistors, right? Both are providing me 180 degree phase shift. So total 360 phase shift I've got already. Then why to use Wein bridge? Okay, Wein bridge is more sensitive to only one particular frequency. For the signals which is having one particular frequency, it is more sensitive. Okay, it becomes more sensitive to the signal with one particular frequency. Okay, we are going to see now. And at this particular frequency, what happens is that the phase shift is 0. Okay, and if the phase shift is 0, I say that my bridge is balanced. That is the most important thing whenever I deal with bridges. Okay, I require the balancing condition. Okay, so I will say that at one particular frequency the phase shift is 0, and whenever this happens, that time I would say that my bridge is balanced. Okay, now say suppose Wien bridge was not used. What would have happened? Output of Q2 would have been given directly to Q1. Okay, and Q1 will amplify over a wide range of frequency. And when I say wide range of frequency, it leads to frequency instability. So that is the reason, to make it more stable, I use Wien bridge network, which will improve the frequency stability. I hope this is clear to you all how Wien bridge offers frequency stability. Now let's go to the mathematical analysis. Still the construction is not over, but I require mathematical analysis for the construction. So let's begin. This is a Wien bridge and this is a general bridge circuit. Okay, I've just put Z1, Z2, Z3, Z4. So now let's compare this. I have Z1. Z1 over here is R1 in series with C1. So I can write this as R1. Z1 is equal to R1 plus 1 upon j omega C1. Similarly, Z2, okay, this I can solve further. I'll take j on top, it will be j upon omega C1, provided you put minus over here. Okay, now next I'll consider Z2. Okay, Z2 is R2 parallel C2. Okay, R2 parallel C2, I can write this as R2 parallel 1 upon j omega C2. Solve this parallel combination. So I'll get somewhat this way. Okay, you all can verify after solving. Now I have Z4, which will be same as R4. I have Z3, which will be same as R3. Okay, so I have got all four things for a Wien bridge. Now what is to be done? Once you consider all the impedances for a bridge, you have to use its balancing condition. Okay, so the bridge balance condition, Z1 Z4 is equal to Z2 Z3. I have got all these things, substitute. Okay, Z1 Z4, it's put up over here, not to worry. Okay, Z1 is this, right? Similarly, Z4 is R4, Z2 Z3, this is Z2 and this is Z3. Solve this again. Okay, solve this and solve and get what? Arrange it in such a way that I get real terms and I get imaginary terms. Okay, and call that equation as equation 1. Now let us start. Once I get a real and imaginary term, I'll now put real term first as 0 because it's easy to solve. Okay, I've got this. Okay, equal to 0. Now divide this equation by R2, R4. I will get this. Okay, just solve and check. Call this equation 2. Now take imaginary component equal to 0. Imaginary component equal to 0. Solve for omega. Okay, solve it. You'll get frequency of oscillation from this. I'll use the condition wherein R1 is equal to R2 and C1 is equal to C2. Okay, I've used this particular condition. Substitute it in equation 3 and equation 2. Equation 3 will become this. F is equal to 1 upon 2 pi CR. You can verify over here. Similarly, equation 2. Okay, if at all I substitute R1 is equal to R2 is equal to R, this will get cancelled. I'll get 1. Similarly, if I put C1 is equal to C2 is equal to C, I will get 1. So minus 1 if I take over this side, it will be 1 plus 1, which will be 2. So R3 upon R4 will be 2. So R3 will be 2 times R4. Call that equation 5. So I've got this condition. Now I'll be back to the construction. Okay. Now initially I had mentioned it to you all that I have used multi-stage amplifier which has Q1 and Q2. The purpose of Q1 is to act like an oscillator come amplifier. Q2 is to act like inverter come amplifier. Okay. So 180 degree phase shift, 180 degree phase shift, total of 360 degree phase shift. Now, in this particular circuit, there are two feedbacks used. Okay, usually in oscillators we just use positive feedback, but there are two feedbacks which are used over here, that is positive feedback as well as negative feedback. The positive feedback is provided by this R1C1 and R2C2 given to the base of Q1, and the negative feedback is provided by R3 R4 given to the emitter of Q1, okay, which is acting like a voltage divider. Now, why do we require this positive feedback? Okay, to explain that, what I have done is that I have rearranged the circuit. Okay, the bridge circuit, I have rearranged it. Okay, this bridge circuit, I have rearranged it over here. Okay, you all can just verify it is correct. I have verified it. Okay, this is my bridge circuit. Fine. Now, just look at this R3 and R4. Why negative feedback is required? That's what I'm supposed to answer now, because positive feedback is required only in oscillators. Why negative feedback is required, that we'll see. Okay. First of all, just have a look over here, R3 and R4. Okay. R3 is connected to the output over here and R4 is connected at the emitter over here. Fine. I'll use the analogy of op amps. Okay. It's an amplifier circuit, right? An op amp is also an amplifier circuit. So this is my feedback resistance. Okay. Now, if I consider the input over here and output over here, they are in phase. Okay. Because here it will be out of phase. Again, it will be in phase because another 180-degree phase shift is provided. So this output and this input will be in phase. So I can say that I have considered a non-inverting amplifier. So for non-inverting amplifier, I have RF which is connected between output and one of the points over here. Similarly, output and one of the points over here. You have R1 which is connected to ground at that point and ground over here. So R3 is like RF, R4 is like R1. What is the equation for non-inverting amplifier? Closed loop gain is given as 1 plus RF upon R1. Similarly, I can write over here A is equal to 1 plus R3 upon R4. I hope this is clear to you all. Then what is R3 by R4? We have just derived in the previous slide, that is R3 is 2 times R4. Just substitute, you will get 1 plus 2 which is 3. So you get gain as 3. Now you know that multi-stage amplifier will produce quite a high gain. Okay, definitely gain will be larger than 3. So what I need to do is I need to reduce this gain. Okay, to reduce this particular gain, I will use negative feedback. Okay, I'm back to my network. Okay, just to explanation purpose, I had shown that. Okay. So to reduce the gain, negative feedback is used without bypassing R4. If at all you see at this particular network, there is no CE over here, which is the bypass capacitor. It's not used over here because I want that feedback to be given. Okay. So negative feedback should be there. So R4 provides me that negative feedback, which will try to reduce the gain, okay, in order to ensure the gain stability. Okay. And there will be no distortion. Fine. So more gain stability can be provided by R4 by using non-linear resistance. Okay, for example, a lamp, okay, which depends on light. So a non-linear resistor is used. What will happen? We'll just have a look. Loop gain depends on the amplitude of oscillations. Okay, so if at all the amplitude is increasing, what will happen is that if at all the amplitude of oscillation is increasing, more current will flow through this R4, and if more current flows through this R4, what will happen is that it will result in more negative feedback. And you know the property of negative feedback. More the negative feedback, more will be reduction in gain. Okay, because negative feedback reduces the gain. So that is the reason you have more reduction in the gain, and if there is more reduction in the gain, definitely gain will be stable. Okay, it will be reduced and controlled now. Fine. In this way, this circuit provides gain stability. Now let's have a look at the working of this particular circuit. Okay. So you have same way how we had started with RC phase shift oscillator. If fluctuations in VCC are there or there is noise being produced in Q1, it results in random fluctuation in the current IB, okay, which is given to Q1, which will amplify and provide 180 degree phase shift and provide it to Q2, which is gonna further amplify it and provide another 180 degree phase shift, which is being fed back over here, fed back between points A and C. Okay, now when I say it's fed back, part of this feedback signal is given to R4, which will result in negative feedback. I explained in the previous slide also. And part of this feedback is given to R2C2, which will result in positive feedback. But a care is taken in such a way that the positive feedback is more as compared to that of negative feedback. Okay, because it should act like a oscillator. Fine. This is it with the working. This is some of the advantages and disadvantages. You all can just go through. Disadvantage, definitely too many components. I had to explain a lot also. Then advantages, definitely you can change the frequency of oscillation by making use of resistors and capacitors, the variable ones. Now, so many oscillators you all have studied. With this, the Wein bridge oscillator is over. Okay. So many oscillators you all have studied, but how to select the oscillator now? Which oscillator is to be used for which application? Okay. First of all, frequency range. Whichever frequencies you want to operate in. Say suppose you want to operate in high frequencies, you will use LC oscillators. Low frequencies you can use RC oscillators. Power and voltage requirements. Say suppose you want larger voltages. Okay, larger voltage. Then definitely you should go for Wein bridge. I mean to say RC. Then amplitude and frequency stability, we have just discussed in the previous slides. Waveform distortion, it should produce less distortion or no distortion. And finally, output impedance for maximum power transfer, because oscillator is not the only circuit. You are going to connect that output sinusoid to some other circuit. So impedance matching should happen so that maximum power transfer can take place. These are some problems for practice which are very easy, you all can solve. These are the references, 3 textbooks I referred. Thank you.